Hey, good morning, everybody. As we're kind of gathering today, I just wanted to give everybody time to kind of get settled in, and I'll introduce our center real quick before we get into the actual workshop today. If you are here for the multiple imputation and practice workshop, this is the right place. Welcome aboard. My name is Paul Schultz. I'm a statistician and data scientist here at the Population Dynamics and Health program here at the University of Michigan in Ann Arbor, Michigan. So we've got people sort of from all over the world today. That's pretty normal for these online workshops. So again, I'm not sure exactly where you are, but welcome aboard today. Before I get into the meat of the workshop, I just wanted to kind of take a couple minutes and plug our center really fast. We've got a kind of a small center here at the Population Studies Center within the Institute for Social Research here at the University of Michigan. And we are funded by a National Institute of Child and Health Development grant to do these free workshops. And so I wanted to take a minute to thank our funder for doing that, and just kind of describe some of the services we offer. So we are a population studies center here, and we're charged with supporting population researchers that are seeking funding through the population dynamics branch at NICHD. So if you're in that area, feel free to check out our affiliateship program. Just a quick set of highlights of what we do. We offer a small grants program that you can seek funding. We also offer a career development program where we can embed our affiliates with sort of more successful scientists to kind of help get your career kickstarted if you're an early career scientist. And then we also offer various technical services, which is what I personally work on. And so we've got a team of analysts here that we can deploy to your project to help with sample design, experimental design, machine learning, web scraping, really any technical aspect of your research that you might need help with. We offer free consulting to our affiliates, and then we also have analysts available to deploy to your project to actually help you do work directly if you need that. So, this is just a quick overview. I encourage you, if you're interested in this type of thing, just poke around our website. Everything I just mentioned is available here. And so if you're interested in any of those things, just please take a look at our website. I'll be lurking in the background of this workshop. So if you have questions about anything, please feel free to pull me aside. And obviously you can reach out to me anytime if you want to inquire further. So that's the quick intro to our center. Thanks for listening to that. Turning our attention to the workshop today. I'm very excited to have this workshop. This is going to be a really important one for me personally, hopefully for you as well. And so just some sort of general sort of tips for the workshop itself. We are recording, obviously. One of the big things we'll produce out of this is a video product that will actually go on our website for all time. And so, if you ever want to revisit this content later, the video will be on our website. But what comes with that is you're being recorded right now. We encourage you to keep muted both video and audio by default, unless you're asking a question. So that way we keep the video more clean. If you do anything weird that you don't want on camera, you won't be captured. And that's the best way that we do that. And so, other than that, feel free to ask questions. The chat is open. I'll be monitoring the chat today. And then I'll defer to our speaker about how he wants to handle questions. But please go ahead and chat those in. If you do have questions, chat them in, and then we'll answer them as we get a chance to. So with that, I'll introduce our speaker and I'll hand off for the day. So our speaker is Trivalor Raghunathan. I'm sure I butchered that. I'm sorry. He goes by Raghu. That's the only way I know him. So I'll let him tell you how he wants to be called today. But he is a research professor in the Survey Research Center here at the Institute for Social Research. He's also a professor of biostatistics at the School of Public Health at Michigan, and is also a research professor in the Joint Program in Survey Methodology at the University of Maryland. He is an associate director of the Center for Research in Ethnicity, Culture, and Health, and he received his PhD in statistics from Harvard University in 1987. His research interests are in the analysis of incomplete data, multiple imputation, Bayesian methods, design and analysis of sample surveys, small area estimation, confidentiality and disclosure limitation, longitudinal data analysis, and statistical methods for epidemiology. And then he has also developed a SaaS-based software for imputing missing values, which you're going to get very familiar with today. So with that, I'll hand over to our speaker, Raghu, and I appreciate you all being here. Thank you.
Thank you, Paul, for that introduction. And yes, I think everybody calls me Raghu, so please feel free to call me Raghu. So I want to welcome you all, and I see that people are coming from all over the place, some familiar names, and welcome to this workshop. So what I plan to do is to give you a brief introduction about the multiple imputation, and then we will also talk about how to do multiple imputation and how to draw inference using the multiple imputation using the software IVEware. There are many softwares that are available, so I'm going to focus on IVEware. And if you have any questions, please put them in the chat, as Paul said, or you can use the raise hand feature, and therefore it will pop up. And then if you have any clarification questions, then we can answer that way too. So either way is fine. So without delay, let me start. Let me share screen. I hope you can see my slides. So this the set of slides that I've put together is sort of adapted from the course that Rod Little and I have taught over several years now. We have taught 2-day short courses, 1-day short course, half-a-day short course, and semester-long courses as well together. And these slides are adapted from that, from those set of slides that we have used over the years. If you are really looking for books, I think most comprehensive book on missing data, covers a wide variety of topics, will be the book by Little and Rubin. And I strongly recommend that. I think if you want to really understand all about missing data in a comprehensive fashion, that's a Little Rubin book is the kind of a foundation for many people in the missing data world. These two books that I have written, one with a co-author with Pat Berglund and Peter Sorenberger, that book uses mostly the IVEware, and it gives a lot of examples and so on. And most of the examples that we'll be talking about are derived from that book. And the material for this course is also derived from this book on missing data analysis in practice. And if you're an R fan, I think my good friend Stefan Buren has an excellent book on flexible imputation of missing data. These three books are much more practice-oriented books with lots of examples and codes. But of course, if you're really interested in doing research on multiple imputation, you have to go to the whole source, which is Don Rubin's book on multiple imputation for non-response in surveys. That kind of provides a really excellent theoretical foundations, as well as sort of a heuristic information about the whole notion of multiple imputation. So I would strongly recommend that that you look through that book if you're really interested in knowing the underlying theory and problems that are yet to be solved. And many of these exercises are excellent source for doing more research in this area. So let me begin with an introduction of what are we talking about? What is the missing data? So there are a lot of examples of missing data. There are two kinds of missing data people talk about, and I'm going to talk both of them. And also this distinction is sort of a little bit more superficial in the sense that I think the methods developed for one could be applied for the other as well. To me, I think the best is to take an example. So I work a lot with the NCHS data set, National Center for Health Statistics data set. So the National Health and Nutritional Examination Survey is a population-based survey that collects a lot of information. They collect information on using the questionnaire. They also do a medical examinations, and they also draw specimens and then get laboratory testing for those things. So one of the national treasure for health-related research. So they also produce the public use files, and these public use files are subject to unit non-response. The unit non-response really implies that the person has did not participate, although it was recruited into the sample, did not participate in any of the activities, so questionnaire or medical examination or laboratory testing. So the unit non-response, so that's kind of a missing data where you have the entire record is missing. And they could be because they have not been able to contact them, non-contact, or they refused. They contacted, but then they refused to participate in that study. So now you could have a different kinds of unit non-response here in the National Health and Nutrition Examination Survey, is that they could participate in the questionnaire, but not in the medical examination. And they could participate in questionnaire and medical examination, but not participate in laboratory studies. So if you look at individually these three components, questionnaire, medical examination, and laboratory, you can say that, well, each one has a unit non-response. So on the other hand, the item non-response is that questionnaire interview is complete, but a health examination is missing. So individually, health examination, you might think that it's a unit non-response, but if you look at it from the entire record perspective, it could be item non-response. So item non-response really indicates that we have a partial information on each individual, on the individuals. So the definition of item non-response, unit non-response gets murkier when you really talk about what relevant variable you are trying to analyze. Now, it's also that in questionnaire, there may be some individual items that are missing. So that's also an item non-response pattern. So generally, I think these item non-response patterns are called as Swiss cheese patterns. So if you check it, Swiss cheese, it holes all over the place. So it's kind of that's the kind of data set that we will be analyzing, and how do you make sense out of that? So the main important thing is that in the unit non-response case, for example, that unit non-respondents, the people who did not respond, may differ from respondents, leading to non-ignorable missing data and biased estimate for the population quantity that you are interested in. So for example, if you take the simple formula of the population mean, so when you take the mean of the respondents and take expectation of that is called as Y bar R. That is kind of a averaging to the estimates of averaging to the values of the respondent mean. But your goal is to estimate the population mean Y bar. So the difference between the respondent mean and the population mean is made up of two components. One is the non-response rate. So non-response rate, pi NR, times the difference between the respondent mean and the non-respondent mean. So the bias is made up of these two components, non-response rate, as well as difference in between the respondents and non-respondent means. Now, in the survey methodology field, there have been two kinds of approaches for dealing with this bias issue. One is to decrease the non-response rate, so pi n r. The other one is to sort of make adjustment for the difference between the respondents and non-respondents. So the adjustment is for the second component to make sure that you have enough of the adjustment that you make so that the difference between the respondents and non-respondent mean becomes smaller. And then strategies for improving this response rate is to decrease the non-response rate. Now, you are never going to have 100% response rate, even after enormous effort that you make. So it's important that whatever strategy that we use, we apply in a way that it affects both components. So not just reducing the non-response rate, but also with the view that whatever we do, we should also be trying to reduce the difference between the respondents and non-respondents. So therefore, it's an important that whether we do a non-response follow-up or we do some other strategies for improving the response rate, we always take into consideration that what survey variables that we are really interested in and whether or not our strategies are going to affect that survey variables of interest. So one approach is to follow a subsample of non-respondents with special efforts. So like you could do an abbreviated interview, or you could have monetary incentives. Monetary incentives, or the variety of other choices people make. So I don't know why the cursor. So I think it's a pretty slow, something is slow. So data collected can be used to, of course, the weighting is a strategy that people use for the unit non-response, which we are not going to talk about much in this workshop, but you can also use it to multiply impute the other non-respondents. So that's why I think it's important that whatever strategy we use, we want to make sure that we are not only increasing the response rate, but also making sure that whatever the strategy is, we will be able to use it to reduce the difference between the respondents and non-respondents. In fact, that's a way to reduce the non-response bias. So it's not that it's increasing the response rate will decrease the non-response bias, because you could actually, in fact, you can increase the response rate, but increase the non-response bias. Because, for example, you increase the response rate, but you are really getting more and more people who are in the some sections of the Y-bar R camp, or in the respondent camp, that really pulls the difference between the respondents and non-respondents even further. So in fact, sometimes I think that's why I think people going for easy cases, like who are most likely to participate in the study and then go for them, might increase actually the non-response bias. So the strategy has to be to reduce the non-response bias. That means the difference between the respondents and non-respondents have to be reduced. So the item non-response generally leads to sort of a Swiss cheese pattern of missing data. And the weighting does not work well for this particular pattern. So imputation is the usual approach. And then multiple imputation is to propagate the imputation uncertainty. The imputations are not real values, so they are made up values. So therefore, there's uncertainty associated with those imputations. A multiple imputation is one way of propagating the imputation uncertainty. There are many other ways in which you can propagate the imputation uncertainty. The multiple imputation is one easier way of doing that in the uncertainty. So some examples, for example, in the attrition in the longitudinal survey, they could move out of the study catchment area, or they could be participation becomes too onerous, so therefore they won't participate. These kinds of in the longitudinal studies can be viewed as an item non-response when you concatenated file for the repeated surveys over time, and you kind of what is called as a long form data, which can be considered as an item non-response. But if you're looking at the cross-sectional analysis or a particular wave, then you might consider that to be a unit non-response. So if you think that the difference between unit non-response, item non-response is more a superficial, and whatever strategy we use for unit non-response can be sometimes adapted for the item non-response, and the strategies we use for item non-response can be adapted for unit non-response as well. So what are the common analysis problems? The complete case analysis is biased if dropouts differ. And sometimes when people use some naive imputation, like a mean imputations, or in a longitudinal context in the clinical trials, the people used to use the last observation carried forward. They involve sort of a unrealistic assumptions. So this is an important component of doing any missing data analysis. Every missing data analysis approach involves assumptions. So there's no assumption-free missing data problem, because you're talking about something that you don't know. Therefore, you have to make some assumptions about what you don't know. And so it's important to find out what the assumptions are and see whether they're sensible or not. So the mean imputation is unrealistic because it says that everybody has the same value. And that's not true in the real world. The last observation carried forward says that, well, after they drop out, nothing changes. They are exactly the same. That's also not realistic assumptions. So we'll talk about the better alternatives.
Raghu, we do have one question that just came in.
Okay.
It says, how do we establish the boundary between incentive and inducement in survey research? Are there chances that monetary/material incentives might infuse unintentional bias to survey response? Do you want to address that?
Yes, it's an excellent question, because I think that's why I think the many IRBs are concerned about the incentives, or whether the coercive effect of the that induces certain sections of the society to participate more than the others. Therefore, that creates a bias to the survey. So that's why I think the best thing is to sort of to study, well, what kind of people are you missing? You know, for that you need to have a good background information, and then see what can you do in a non-coercive way to encourage more participation from the kinds of people that you are, that's underrepresented in your but that's why I think, you know, people have done experiments in terms of different levels of incentives and see what kind of people you get across those different kinds of incentives. So you could give $5, $10, $15, $20, or some sort of a designed experiment is a way to really see whether or not by increasing the incentives are you getting different kinds of people in your sample. So randomized experiment is one way of doing that. I don't know whether that answers the question, but that's a way I would address that issue of is the incentive is producing more differential kinds of people coming into the survey. In relation to the survey variable of interest. That's what we are mostly interested in. Good. I don't know why my screen share is slow. Is it a slow because
Everything looks fine on my end. I guess I can only speak for myself, but I haven't noticed anything on my end.
Yeah, because my screen is not going fast enough. So when I press the arrow,
yeah, everything's pretty fast here at Thompson Street.
okay, I'll go with the not the arrow button, but this. Okay, there are also other problems that can be formulated as a missing data problem. So for example, if you are really interested in finite population inference, so from a missing data perspective, you have a finite population, you draw a sample of units from this finite population. The non-sampled units from the population are missing. So in that case, you could use the missing data techniques that we'll be talking about for the finite population inference. Response errors, like there's a true underlying measure that you are trying to get, but the measured variables are subject to errors, and where true or missing and are only observed for a calibration sample, that also introduces sort of a missing data problem. I talked about disclosure limitations. So replace some values by imputation to reduce the disclosure risk. So that also can be treated as a missing data problem, as well as the inference for causal effects. So if you have a randomized experiment, you have a treatment and controls, and then you get to observe treatment data on people who receive treatment, and you observe control data on those people who receive the controls, but that's kind of a missing data problem as well that you can solve them. So it's kind of a missing data as a framework. You can use that to solve many different kinds of problems. So what is a missing data definition? How do you define what is a missing data? So if filled in, I'm going to give you kind of a heuristic definition of missing data, and you'll see that it is very analysis specific. So always assume missingness is hiding some meaningful value for analysis. If filled in, is it meaningful for analysis? So let me take example. So missing data from a missed clinical visit. That definitely is a missing data problem. Now let's take a little bit more complicated problem. Non-response in an opinion poll. Somebody says, I don't know. You ask a question, are you going to vote for candidate A or B? And people say, I don't know. Is that a missing data problem? Yes and no. No, if you're really interested in analyzing that who are the people who say don't know versus the people who say that they are going to choose A or B. So in that case, the don't know is an important component of your measurement itself. So there's no missing values there. Don't know or a response category you are really interested in. On the other hand, suppose if you are really projecting whether A or B is going to be the elected or going to be winner, then these don't know are hiding the meaningful value that whether or not they're going to vote for A or B, or they're not going to vote at all, right? So there's an uncertainty in terms of whether or not they're going to vote for A or B, or they're not going to vote at all. So from the projection perspective, yes, there is a don't knows or hiding a meaningful value for the analysis. So therefore, it is a missing data problem in that projection context. But in the context of explaining the differences between people who have made the decision versus people who have not made the decision, then don't knows are not a missing data problem. Don't knows are part of a response category. So the definition of missing data is specific to that analysis that you are really interested in. And if you think that it's a meaningful value for the analysis, then it is missing data. So if I take a longitudinal study of blood pressure medication, if people have lost to follow-up, if they're alive, then you know that there is a missing data problem, because you don't know what actual their blood pressure medication uses or blood pressure is after they have dropped out. If they are dead, then it is not a missing data problem. Dead people don't have blood pressure. So we don't know. That's kind of a different kind of a problem, that deaths are not considered to be missing data in that context. Now, you could turn it into a missing data problem if you were really answering the question, if they were alive, what would have been their blood pressure? And that's kind of a, many times in a kind of a competing risk model that you talk about, that a person had a disease A and died, and you want to know what would have happened to that person if that person hadn't died of the disease A, and what would have been the chance of getting the disease B. And sometimes that you kind of speculate those kinds of analyses. So whether even in the context of death, you might say that, okay, now I want to know what would have happened. But generally, in an observational analysis, deaths will not be considered as a missing data problem. So what is a pattern of missing data? So some methods work well for general pattern of missing data. Here's the cases where variables, cases are the rows and the variables are the column. And this is kind of a very general pattern, the Swiss cheese pattern. Now you might get other special patterns of missing data. So for example, you might have a monotone pattern of missing data. This is more common in a longitudinal analysis. So you have a wave 1 data, and you have a wave 2 data is available only on a subset of people who completed the wave 1 data. And generally wave 3 data, you go only to subset of the people who participated in wave 2, and so on and so forth, which is kind of a bad strategy, because you want to go back to the original wave, original data sets, original sample anyway, even in a longitudinal study. But sometimes when you just go only to those people who gave you the data in the previous wave, then you get what is called as a monotone pattern of missing data. So sometimes even in your data set, you can rearrange the columns and rearrange the rows in a way that it generates a kind of a monotone pattern of missing data. Now, univariate missing data is a case where you have everything else is available, but only one variable is missing. So sometimes you come across these kinds of a specialized situation in a particular analysis. The file matching kind of pattern is that this is a kind of a pattern that comes in when you're piecing together two data sources. You have a variable X and Y measured from the data set 1, and you have a variable X and Z measured in variable 2 in data set 2, and you have them fusing them or you're concatenating them, you get this kind of a file matching kind of missing data pattern. So general pattern of missing data, we are focusing on this course. Multiple imputation for item non-response works very well, but there are other methods that are available for when you have a specialized set of patterns of missing data. So the pattern says which values are missing. Before we proceed with any method for the analysis, we have to know why. Why are they missing? Are the reasons related to the study variables itself? This is formalized by model or mechanism. So Y is a data matrix if no data were missing. So let us say imagine the data set, you have N subjects and P variables, and this data matrix is N by P matrix. That's what you would have ideally observed if there were no missing data. Now, missing data indicator matrix is as if ijth element is 1 if it is missing, or 0 if it is observed. Sometimes I will use the response data indicator matrix, which is kind of a complement of that. Response indicator matrix will be 1 if it is observed and 0 if it is missing. So the missing data indicator matrix is sort of which ones are missing and which ones are observed. So patterns are really concerns about the marginal distribution of M. Is that what is the distribution of the missing values in the data set? Situations, where are they missing? The mechanism is about the conditional distribution of M given Y. So why are they missing? So what is the relationship between their missing data indicator matrix and their underlying measurement Y? So we say the data are missing completely at random if missingness is independent. If missingness is independent of Y. So that means the conditional distribution of M given Y is P of M for all Y. So this is kind of saying that the it's completely at random. It's kind of a, if you think of this as a design of experiment context, it's kind of a completely randomized design. The treatments have been assigned completely at random. So if you think of missing data or kind of a treatment assignments that are assigned at completely at random. So it's kind of completely, that's a kind of a missing completely at random comes from that design of experiment language, where if you think that they are throwing away this dart of missing data indicator matrix on the Y matrix, they kind of randomly landing wherever they want. It has nothing to do with the underlying Y measurement in the data set. And if you drop out all the cases with missing values, generally that's an assumption that you are making, missing completely at random. That is, the people who are missing values are very similar to people who have no missing values. So that's a general assumption that you're making when you're doing a complete case analysis or just dropping out all the people with missing values. So missing at random, which might think like it's similar to the missing completely at random. Missing at random is the missingness can depend upon anything that you observe. So depends on the observed components of Y-ops. So let us take an example. Suppose that you are doing a study where you're collecting the income data. And you have age, education, age, gender, education, occupation, and income. Now, missing completely at random says that the people who are missing income have nothing to do with any of the variables in the data set. Whereas missing at random says missingness, suppose that there's no missing values in age, gender, and education and occupation. And income has some missing values. So missing at random says that the missingness in income can depend upon age, gender, education, and occupation, but it cannot depend upon income itself, the unobserved income itself. So if you're talking about the design of experiment language, this is kind of like a randomized block design. So you're creating the blocks based on age, gender, education, and occupation, and you create the blocks. Within those blocks, the people with missing and non-missing income have the same distribution. That's an assumption that you're making in that. So it's kind of a more closer to kind of a randomized block design where you can group the respondents and non-respondents in a way that in that group, the distributions of the people with income who gave you the income, who did not give you the income, their distributions are the same. Missing not at random means that missingness, even after creating those blocks, the missing values, the distribution of those with missing income is different than those with no missing values. Now you can see that both these assumptions, missing at random and missing not at random, are unverifiable assumptions. Because within the block, I'm making the assumptions that the respondents and non-respondents have same distribution. And missing not at random, I'm saying that within the blocks, respondents and non-respondents have different distribution. In one case, I'm saying the null hypothesis is true. That is, the distributions are the same. The second, I said the distributions are different. But I don't have data on non-respondents. So because I don't have a data on non-respondents, I can never say whether they're equal or not equal. If they're equal, I have to assume that if they're equal, go on. If they are not equal, then I have to specify how they are not equal. But I don't have any data for that because I don't have any data on non-respondents. Therefore, that is also unverifiable. I can make something up. Oh, people with high income are not participating. But there is no way I can specify that relationship because I don't know the missing values. I don't know the income of those people, of non-respondents. So the missing at random and missing not at random, both of them are unverifiable assumptions. Now, I can assess whether it's missing completely at random because I have some Y, so I can say age, gender, and education, occupations available. I can look at the relationship between M and those variables. And if there's no relationship between M and those variables, then I may say that, well, conditional on these variables, I don't see that there is a bias in the people who responded versus who did not respond. In saying that the distribution of these variables seems to be similar across those respondents and non-respondents groups. But missing at random and missing not at random, both of them are making unverifiable assumption in that case. Now, The key is that what you're conditioning on. So in the example I said about the income, I have age, gender, and then I have education and occupation. If I had only age and gender, I am making a stronger assumption about the missing data mechanism than having age, gender, and education. And I'm making a stronger assumption having just the age, gender, and education, but weaker than just using age and gender. Now, age, gender, education, income, education, and occupation, conditioning on those 4 variables, I am making a weaker assumption than just the age, gender, or age, gender, education. So more I condition on variables related to the income, the weaker the assumption about the missing data mechanism. So that means that I'm creating more and more refined blocks so that the distributions of the income within those blocks for the respondents and non-respondents becomes much more palatable. Similarity of those things. So null hypothesis is more likely to be true. So it's not about just about this assumption, but also I think what kind of variables that you have in order to condition on. So in the imputation world, we try to condition on as many variables as possible in order to make a weaker and weaker assumption about the missing data mechanism. And the missing at random assumption is by conditioning on larger number of covariates that are related to the income, you are making a weaker assumption. So if you have a missing at random for a, that's considered a univariate non-response. So xj is a complete covariate, M is missing, M is 1 for Y that's missing, and 0 if it is Y is observed. The response indicator is that 1 minus M. So the missingness is independent of Y given x1 to x3 or x1 to xk. That is, M can depend upon x's, but not on Y given x. So for example, if your MAR, if dropout depends on the values recorded prior to dropout, it's missing at random. Missing not at random means if dropout depends on the values that are missing, that is after the dropout. And again, as I said, there is no way to distinguish between these two from the observed data set itself. Censoring by the end of the study is possibly missing completely at random. So probably my funding ran out, so I had to censor everybody. So that's possibly missing completely at random. So drop out from a panel study because they moved to Arizona. MAR, if the reason for moving, for example, age is captured as a covariate. And it may be MAR for health survey. So it depends, depending upon what kind of covariates you have. If you have a health is measured, then you can conditioning on that health, then it could become missing at random. If you take a non-monotone pattern of missing data, if you have a Y1 and Y2, then on some cases you have Y1 observed, some cases you have Y1 and Y2 observed, in some cases you have only Y2 observed, then the probability that Y2 is missing can depend upon Y1. So probability that Y2 is missing is a function of G of Y1, and probability that Y1 is missing can depend upon Y2. And that this really means that the probability of being complete is an additive function of Y2 and Y1. So this is a kind of a missing at random mechanism that whatever is observed can predict their missingness. Whatever is not observed cannot predict their missingness. That's an example of a monotone. Now, there are 3 general strategies for dealing with missing data. So the first strategy is the imputation, which is what we will be focusing on. And then the other case is to develop sort of weights for complete cases. Somehow use these weights to compensate for the people who are being eliminated because of missing values. As I said, this is much more doable in a simple patterns of missing data, or for example, in the monotone pattern of missing data, or you can do it for the univariate pattern of missing data, some other missing data pattern. But if you have a very general pattern of missing data, it's much harder to do these weights. The other approach is to analyze incomplete data by using sort of a methods like maximum likelihood or fully Bayesian methods. But you will see that the multiple imputation method is sort of kind of, you can view that as an approximation for doing maximum likelihood or doing the Bayes under certain conditions. So you can see that the imputation-based method, multiple imputation methods, and the analysis of incomplete data using maximum likelihood Bayes are kind of close to each other. You will see that. So in this course, in this workshop, we will be focusing on imputation-based approaches. Now, regardless of which method you use, there are some good properties of good missing data methods. You have to make use of partial information on incomplete cases. So you might want to make sure that you are using as much information as available on that individual in order to reduce the bias and increase the efficiency. And whatever method we use should be calibrated. That is, inferences that are valid under the plausible model for missing data. So for example, the confidence intervals have to have nominal coverage. If I say it's a 95% confidence interval, it should be 95% confidence interval. It should propagate the missing data uncertainty. You could use multiple imputation models. So regardless of whether you use a one imputation model or two imputation model, you have to propagate the uncertainty because of imputation. And that's why I think sometimes feel very leery of people just imputing once and releasing the data, and people going and analyzing the data as though it is the actual data. That really underestimates the uncertainty, and standard errors are really wrong in those cases. And that's why I think multiple imputation and incorporating the uncertainty is very, very important. Now, if you are able to, then maybe you can do maximum likelihood method, but multiple imputation is more kind of a close cousin or approximation of the maximum likelihood and Bayesian method that we will be talking about. Okay, any questions?